Yeah, hi, folks. Let's take a peek at a game now where we can begin to see whether iterative elimination of strictly dominated strategies has any bite in application. And in order to do this, we're going to look at an experiment that was done by Baldwin and Mies in the late 1970s. And they were actually looking at social behavior in pigs. So the players in our game here are going to be pigs. There's actually sort of an interesting discussion of this. This comes from Joe Harrington's book, Game Strategies and Decision Making. And the idea is sort of interesting. You've got two pigs in a cage. Okay, so they're in a cage, a several meter cage. One of the pigs is larger than the other. We'll call that the dominant pig. Sorry for the terminology, so we'll actually use the word, say, the larger pig. What they need to do is food arrives, but they need to press a lever to get the food to arrive. Okay, and the critical thing is that the lever is on one side of the cage. So you go over, you press the lever, and then the food arrives on the opposite side of the cage. Okay, so the pigs are put in a cage. The cage, they learn eventually that if they hit this lever, food appears on the other side. So what they would have to do is, if they want to eat, they would have to move over, run up to one side of the cage, hit the lever, run back to the other side, get the food that comes out, eat the food, a few pellets of food, then they go back, hit the lever again, run back to the other side of the cage, get some food. Okay. Now, the difficult part is that there are two pigs in the cage. So if we put two pigs in the same cage and one is larger, then when they're both trying to get the food which comes out, and these are pigs, the larger one will end up getting the food and the smaller one will get less food. Okay, so that's the basic idea here, and then we can analyze this as a game. So in particular, let's take a look in more detail at how the payoffs work here. So when the food comes out, there's 10 units of food, 10, say, pellets of food that come out. And let's look at what the typical split ends up being if there are two pigs in the cage, one is larger, one's smaller. And if the larger one gets to the food first, then there's basically a 1-9 split. So that means that the small pig ends up with one pellet, and the larger pig would end up with 9 units of the food. So if the large one gets there first, it's very hard for the small one to get anything. They tend to get 1 on average, but close to nothing. If the small pig gets to the food first, then they end up with a 4-6 split. Okay, so then it's 40-60. So the small pig still gets less, the bigger pig still gets more, but the small pig at least has literally a fighting chance here. Now, if they get to the food at the same time, then it's a 3-7 split. So the bigger pig gets a little more. And one other thing is that running over and pressing the lever actually consumes some calories. So let's take that. They take it to, say, 2 units of food in terms of energy. Okay, so we've got these different splits and so forth. So what we can do is write out a simple normal form game for that. So given all these numbers, here's the small pig over here, large pig over here, and now they have two choices. They can either run over and press the lever, or they could sit there and sit by the food side and wait for the other pig to press the lever. Now, if you both go to press the lever, then they get back to the food at the same time. It's going to be a 3-7 split, but it's a 3-7 split, and then you subtract off 2 for the cost of running back and forth. So they each lose 2 units of food. So 3 minus 2, we get the 1. 7 minus 2, we get the 5. So we end up with 1-5 if they both do it at the same time. In a situation where, say, the small pig presses the lever and the big pig just waits there, then it's a 1-9 split, but the small pig ends up losing 2 units in energy. They actually end up with a net negative in that situation and so forth. So you can go through and put this into a normal form game. And what we end up with is a simple matrix form 2x2 game, which looks like this. Okay, so we can analyze this game quite simply. Let's take it and let's analyze it via the iterative elimination of strictly dominated strategies. So what's true in this game? Well, where does anybody have a strictly dominated strategy? The big pig, the large pig, doesn't have a strictly dominated strategy. They would like to wait if the other one presses. They would prefer to press if the other one waits. So no domination here. But notice that the small pig always gets a higher payoff. 4 versus 1, 0 versus -1. They would always prefer to wait. So in this particular situation, the small pig has a strictly dominated strategy of waiting. So we should get rid of press as a strategy for the small pig. And once we've done that, now in what's left, the big pig should press. And so what we end up with is when we iteratively eliminate strictly dominated strategies, we end up with a prediction that the small pig should wait and the big pig should be the one that presses the lever. Okay. So let's look at how they actually behaved, the pigs in the experiment. And so what they did here is they gave them 15 minutes of doing this. They did 10 tests where the pigs were alone in the cage. So the first 10 tests where the pig just sits there for 15 minutes and learns how to press the lever and get food. And then they put the pigs together and do another 10 tests, each for 15 minutes as well. Okay, so what they're doing here is this is the frequency of pushing the lever per 15 minutes. And we can look at what happens when the large pigs when the pigs are separated. They're both alone. There we see roughly the large pigs going about 75 times per 15 minutes, pressing the lever. I mean, these pigs are really moving back and forth to get the food. The small pigs, say 70 times, running back and forth to get the food. So they're both, if they're left alone, they press the lever, they run back and forth. If they're together, then what happens? Well, the prediction was that the larger pigs should do the pressing, right? They should do the pressing, and the smaller pigs should do the waiting. And indeed, how frequently do they push the lever? The small pigs very seldomly, only 5 times now, whereas the large pigs are doing it about 105 times. So indeed, we are seeing them pressing and waiting in conjunction, as predicted by the theory. And in fact, the large pigs are doing more pressing, and partly possibly because they're getting fewer pellets out, since the small pig is sitting there and eating some of the pellets that the large pig is producing by pressing the levers. Okay, so what do we learn from this? Are pigs rational? Do they know game theory? Well, they probably didn't sit down and solve the normal form game and iteratively eliminate strictly dominated strategies. But one thing is true is they do learn, and they did seem to respond to incentives. And I think the iterative elimination of strictly dominated strategies is something which nicely captures learning. So you learn not to play a strictly dominated strategy, right? Because it's always giving you a lower payoff. Eventually, you discard such strategies. So players won't be sitting there playing a strictly dominated strategy if they ever have some experience with other strategies. Once they stop playing those, then you learn not to play strictly dominated strategies out of what remains. So the small pig can learn that it just doesn't pay to run over and press the lever because the big pig gets everything. So they stop pressing the lever. They just sit there and wait. And eventually the big pig does the pressing. So you learn not to play strictly dominated strategies out of what remains. And so the idea here is that learning, evolution, survival of the fittest, these are powerful game theoretic tools. And iterative elimination of strictly dominated strategies in games where there is some power to these things ends up making some predictions which can be quite powerful.
We will now speak about Maxmin strategies. These make particular sense in the context of zero-sum games, but actually are applicable quite to all games. What is a Maxmin strategy? It's simply put a player's strategy that maximizes their payoff, assuming the other player is out to get them. We will concentrate primarily on the two-player case here, again, because when we get to zero-sum games, those really make only sense in the case of two players. But keep in mind that one could define this kind of more generally when we speak about Maxmin strategy. So the Maxmin strategy is a strategy that maximizes my worst case outcome, and my Maxmin value or safety level is that payoff that's guaranteed by the Maxmin strategy. And here it is defined formally. The Maxmin strategy for player I is the strategy S1 that maximizes the minimum that the other player, remember that minus I is the player other than I, would hold player 1 down to. And the Maxmin value is defined similarly to be the value of that Maxmin strategy. Now, why would we want to think about the Maxmin strategy? One can think of it either as a simply a sort of a certain cautionary, maybe the other people will make some mistakes and not act in their own best interest. Maybe I'm not sure exactly what their payoffs are. There are a lot of interpretations, or you can simply be paranoid about them and think that they're out to get you. And you know the saying, even the paranoid have enemies. That's the Maxmin strategy. And just to confuse things, we'll also speak about the min-max strategy. The min-max strategy is strategy against, if you wish, the other player in the two-player game, is a strategy that minimizes their payoff on the assumption that they're trying to maximize it. And so here is the formal definition. The min-max strategy for player I, who's playing against the other guy, which we denote by minus I, is the strategy that minimizes the maximum payoff as attempted by the other guy of the payoff to the other guy. And the min-max value is simply the value of that min-max strategy, the value to player 1. Now, why would player 1 want to harm the other guy? Well, you could just be out to get him. That's a possibility. Or they could be playing a zero-sum game. And in a zero-sum game, hurting the other guy is tantamount to improving your own payoff. And so in the setting of zero-sum games, max-min and min-max strategies make a lot of sense. And in fact, in a very famous theorem due to John von Neumann, it proved that in a zero-sum game, by definition, we consider only two-player such games, any Nash equilibrium, the player receives a payoff that is equal to both his max-min value and his min-max value. And that means that, so we'll call that the value of the game. The value for player 1 is called the value of the game. And that means that the set of max-min strategies are really the same as set of the min-max strategies. That is, trying to improve your worst-case situation is the same as trying to minimize the other guy's best-case situation. And any max-min strategy profile or min-max strategy profile, because they're the same, constitute a Nash equilibrium. And furthermore, those are all the Nash equilibria that exist. And so the payoffs in all Nash equilibria is the same, namely the value of the game. One way to get a concrete feel for it is graphically, and here's the game of matching pennies. This is a game where each of us chooses heads and tails with some probability, and if it comes up either if the result of our randomization, I end up choosing head and you end up playing tail, you win, and vice versa. Also, if I chose tail and you head, but if we both chose head or both chose tail, I win. And so here are the payoffs. You see here the strategy spaces. This is player 2 is kind of increasing their probability of playing heads, and this is player 1, and on this dimension you have the value of the game, the payoff to player 1, and the only natural equilibrium is for both to randomize 50-50. It's just right here. It's conveniently looked by slicing the three-dimensional structure in this way, and you sort of see that it's got to be an equilibrium in the sense that player 1 could be moving along this curve, but as he does it, his payoffs would only drop, and so he's trying to maximize the value. He wouldn't do it, and conversely, player 2 can only traverse along this, but if he does that, the payoffs would only increase, and he's trying to minimize the value. So you get a stable point, which for obvious reasons is called a saddle point. In general, we can use the min-max theorem to compute the equilibria of zero-sum games, and we do it by simply laying out a linear program that captures the game, and here it is. So U1 star is going to be the value of the game, that is the payoff to player 1 in equilibrium. And so we're going to specify from player's 2 point of view. We could have done it the other way around also. So what player 2 is saying is simply says, for each of the actions of player 1, each action that player 1 might consider, I want to find a mixed strategy S2. So here's my mixed strategy S2. It will look at all my pure strategies K and make sure that the probability, that's the probability distribution over those. They sum to 1 and they're non-negative. So what I'd like to do is that the best response to my strategy by player 1 for any of these actions will never exceed this value of the game, because I'm trying to minimize it. So I'm going to find the lowest U that has a property that player 1 doesn't have a profitable deviation by any of his pure strategies. So when I look at the payoff for player 2, when I play A2K and he plays A1J, that J that I'm considering right now, and I multiply the probability of, in my mixed strategy, playing A2K, I don't want that other player 1, to have a profitable deviation. So it's got to be that his expected payoff will be no greater than the value U1 star. So clearly this is a correct formulation of the game, and it is a linear program. As we know, linear programs are efficiently solvable, in theory by a interior method that is provably polynomial, in practice by procedures that are worst case exponential, but in practice work well.